The Internet Protocol. All TCP, UDP, ICMP, and IGMP data gets transmitted as IP datagrams. By best effort, we mean there are no guarantees that an IP datagram gets to its destination successfully. When something goes wrong, such as router temporarily running out of buffers, IP has a simple error handling algorithm. Throw away some data, usually the last datagram that arrived. So IP has that simple algorithm. It's usually being handled more carefully by higher layer such as transport protocol. Any required reliability must be provided by the upper layer like TCP. IPv4 and IPv6 both use this basic best effort delivery mode. The term connectionless means that IP does not maintain any connection state information about related datagrams within the network elements, like within the routers. Another description of connectionless is that the IP does not maintain any connection state information about the related datagrams within network elements like within the routers. If a source sends two consecutive datagrams like first A then B to the same destination, each is routed independently and can take different paths, and B may arrive before A. So that's what we meant by connectionless, since essentially these are being divided into IP datagram. B could arrive earlier than A, and they could get into the same destination in a different hop or in different routers. Other things can happen to IP datagram as well. They may be duplicated in transit, and they may have their data altered as the result of errors. So it can be duplicated as well, aside from altered or error or not being able to receive on transport. And remember, the transport layer has a way to check that using its payload, which we'll gonna discuss later. Again, some protocol above IP, usually TCP, has to handle all of these potential problems in order to provide an error-free delivery abstraction for applications. In this chapter, we take a look at the fields in the IPv4, see figure 5.1, and IPv6, see figure 5.2 headers, and describe how IP forwarding works. Figure 5.1, the IPv4 datagram. The header is of variable size, limited to 15 32-bit words, 60 bytes by the 4-bit IHL field. A typical IPv4 header contains $20, no options. So these are the header. If no options, such as this, it's 20 bytes. The source and destination addresses are 32 bits long. Most of the second 32-bit word is used for the IPv4 fragmentation function. A header checksum helps ensure that the fields in the header are delivered correctly to the proper destination, but does not protect the data. So let's leave it a little bit there. Let's discuss the multiple spanning protocol. I forgot to discuss this just a moment. So sorry, multiple registration protocol, or MRP. The multiple registration protocol, MRP, provides a general method for registering attributes among stations in a bridge LAN environment. So it's a way to remember LAN. It's on top of STP. So an STP should work first before you can implement this. It's basically a way of remembering VLAN attributes or IDs in the network for better organization. 802.1 AK to 2007 defines two particular applications of MRP called MVRP for registering VLANs and MMRP for registering group MAC address. So an MRP called MVRP are used for registering VLANs and MMRP are used for group MAC addresses. MRP replaces the earlier GARP framework. MVRP and MMRP replace the older GVRP and GMRP protocols, respectively. All were originally defined by 802.1q. With MVRP, once an end station is configured as a member of a VLAN, this information is communicated to its attached switch. So if it's configured as a member, it is communicated to its attached switch, which in turn propagates the fact of the station's participation in the VLAN to other switches. This allows switches to augment their filtering tables based on station VLAN IDs and allow changes of VLAN topology without necessarily triggering a recalculation of the existing spanning tree via STP. So after it was propagated, the switch augment their filtering tables based on the station VLAN IDs. So it's kind of like enhancement of the STPs that allow changes of VLAN topology without necessarily triggering a recalculation of the existing spanning tree via STP. Avoiding STP recalculation was one of the reasons for migrating from GVRP to MVRP. MMRP is a method for stations to register their interest in group MAC address. Multicast addresses. So a group MAC address or multicast addresses. So that's what MMRP. This information may be used by switches to establish the ports through which multicast traffic must be delivered. So this information are used by the switches that is member of this VLAN to determine where the multicast traffic must be delivered. Without such a facility, switches would have to broadcast all multicast traffic, potentially leading toward leading to unwanted overhead. MMRP is a layer 2 protocol with similarities to IGMP and MLD. Layer 3 protocols and the IGMP MLD snooping capability supported in many switches. So this is the conceptual diagram. So here is the IEEE 802.1 layer 2 stack. Then we have spanning tree family, the STP 802.1D/RS or RSTP 802.1W, MSTP 802.1Q. These prevent loops, peak paths. So that's what the MSTP does. Here is the MRP or multiple registration protocol. It's IEEE 802.1 AK. MVRP, VLAN registration. It advertised VLAN across bridges dynamically. MMRP, multicast MAC register. Advertised multicast group membership. Then after that, we have Bridge Forwarding Database, FDB, MAC table, VLAN table, updated via MVRP, MMRP, controlled by STP topology. How they connect? STP or RSTP or MSTP controls topology, which links are forwarding or block. It ensures there are no loops and defines the active paths between bridges. MRP or MVRP, MMRP run inside that stable topology. Once that path is defined by STP, MVRP and MMRP tell switches what data should flow on those paths. So they tell switches after or top of STP what data should flow on those paths. MVRP dynamically advertises which VLAN exists on which ports. So the VLAN membership is propagated through the active topology. No need to manually configure every switch. MMRP dynamically advertises multicast group memberships, so multicast frames are only flooded to interested ports. Integration point. MRP frames are layer 2 control frames just like BPDUs. They are carried only along the active tree that STP builds. So they are carried only along the active tree that STP builds. If STP blocks a port, MRP frames will not cross it, preventing loops in VLAN and multicast propagation as well. And in Linux, when you enable BRCTL STP BR0 on, it enables STP logic, and bridge MVRP on BR0, it enables MVRP daemon. The bridge kernel module handles forwarding and STP states. So that's where the STP lies. It's in a bridge kernel module. The MRP, MVRP, MMRT daemons is run in user space. It communicates with the bridge layer via netlink sockets. So we will discuss the netlink sockets in just a moment. When VLAN membership or multicast group changes, MVRP or MMRP send MRP attribute events in Ethernet frames. Destination MAC 01 colon 80 colon C2 colon 00 colon 00 colon 214 MRP. Those propagate to neighbor switches, updating their VLAN or multicast tables dynamically without touching STP. So it used this netlink socket of its kernel via user space daemon or user space application. It sends these MRP attribute events. Summary flow. Now first, STP or RSTP or MSTP decide which links are active. Second, MVRP or MMRP decide what VLANs or group traverse those links. Third, bridge FDB learns actual MACs on those VLANs or group. Result, a loop-free auto-configured dynamically adapting layer 2 fabric. What netlink actually is? Netlink is Linux internal communication mechanism. A kernel, user space messaging channel, not a network protocol on the wire. So it's a messaging channel. Think of it as an invisible local socket, not using IP, used only inside your computer. So in OSI layer context, you have layer 7, user space daemon. This is where the netlink, like BRD, MSTPD, LLDPD, MRPD, network D, etc. It talk to kernel via netlink socket, which is the internal API. So it's not a network protocol, it's an OS, like trapping into a kernel admin functions. So that those where the netlink socket came. Layer 2, kernel bridge driver, bridge.ko, br underscore net filter, handles STP, RSTP, VLANs, forwarding, FDB, etc. Layer 1, NIC driver, ETH0, WLAN 0, etc. In practice, here's what happens when, say, RSTP runs on Linux. First, kernel bridge driver detects an event, like ETH1 link down, carrier lost, interrupt from NIC driver. Second, kernel post an event to netlink, like this code rtnl underscore notify with argument event underscore struct. This send a message to any user space process subscribe to bridge events. So after the NIC raise an interrupt, like a carrier lost, it will drop into the kernel netlink socket that will then drop into the user daemon. That user daemon will then drop into all registered bridges among it. User space daemon like mstpd bridge-stp or mrpd receives it on a netlink socket, reacts and updates STP state. So this mstpd bridge-stp or mrpd receive this NIC interrupt on a netlink socket. It will react and updates STP state, like this code rec v msg argument netlink underscore fd comma end message comma 0 semicolon next line handle underscore port underscore down argument message next line send underscore bpdu underscore update. Daemon fourth daemon constructs bpdu and injects it back to the kernel bridge driver via netlink again. So these are the line of code for the daemon or user space to construct the BDU to be sent back to netlink. Send, these are the code, send msg argument netlink underscore fd comma and bpdu underscore frame comma 0 semicolon. The kernel then encapsulates it as an Ethernet layer 2. So after you send it to its own netlink, its own kernel will encapsulate it to an actual Ethernet frame layer 2 and sends it via ETH0 or ETH1 to neighbor bridges. So its own kernel will be sending those frame. Now TLDR, think of netlink as a local control bus between kernel networking stack and user daemons. Used by IP command, IP link add, network manager, so again, netlink is a local control bus between kernel networking stack or its modules for network and the user daemons that need network access. It used by IP command, IP link add, network manager, system d-network d bridge-stp mrpd lld pd etc. It never leaves your computer. It's not layer 3, not TCP or UDP, not visible in Wireshark. Summary analogy concept: netlink, what it connects, kernel to daemon inside OS, visible on the network, no. Purpose: internal communication. Concept: BPDU, what it connects, bridge to bridge Ethernet L2, visible on the network, yes. Purpose: STP or RSTP topology control. Concept: MRP frame, what it connects, switch to switch Ethernet 2, visible on the network, yes. Purpose: VLAN or group registration. Concept: TCP or UDP, what it connects, host to host L3 or L4, visible on the network, yes. Purpose: data transport. Now let's go back to this IPv6 header. The IPv6 header is of fixed size, 40 bytes, and contains 128-bit source and destination addresses. The next header field is used to indicate the presence and type of additional extension headers that follow the IPv6 header, forming a daisy chain of headers that may include special extensions or processing directives. Application data follows the header chain, usually immediately following a transport layer header. So we will dig into that. IPv4 and IPv6 headers. So figure 5.1 shows format on IPv4 datagram. The normal size of the IPv4 header is 20 bytes, unless options are present, which is rare. So this option is rare. This will add the size of the IP header, but it's rare. The IPv6 header is twice as large, but never has any option. So this header is 40 bytes. And it never has any option to add into it. It may have extension headers which provide similar capabilities as we shall see later. In our pictures of headers and datagrams, the most significant bit is number 0, and the least significant bit of a 32-bit value is number 31 on the right. So the most significant start from 0 and the least are 31. The 4 bytes in a 32-bit value are transmitted in the following order. Bits 0 to 7 first, then bits 8 to 15, then 16 to 23, and bits 24 to 31 last. This is called big endian byte ordering, which is the byte ordering required for all binary integers in the TCP or IP headers as they traverse a network. It is also called a network byte order. Computer CPUs that store binary integers in other formats, such as the little endian format used by most PC, must convert the header values into network byte order for transmission and back again for reception. So these 4 bytes or 32 bits are make up in this following order: bits 0 to 7 first, 8 to 15, 24 to 31 last. So this is called a network byte order. Now computer CPUs that store binary integers in other formats, so for other type of CPU such as the little endian format used by most PCs, must convert these header values into network byte order for transmission and back again for reception. So remember, the CPU or the kernel of Linux are the one converting this into an Ethernet frame to be sent like via Wi-Fi or Ethernet. Therefore, their CPUs must do this conversion in binary integers format to little endian format from network byte order. Now header fields. The first field only I have 2. There you go. Yeah. The first field, only 4 bits or 1 nibble wide, is the version field. It contains the version number of the IP datagram, 4 for IPv4 and 6 for IPv6. So it uses this number to distinguish between IPv4 and IPv6. And though other version has been created, these are the most widely used. The headers for both IPv4 and IPv6 share the location of the version field, but no others. So as you can see, the version for these are the IPv6, these are IPv4, is the same. They say the same. They share the same version and no others. So these are the version for IPv6 version and then DS field immediately. Let's delete this. While in IPv4, you have IHL after the version. Thus, the two protocols are not directly interoperable. A host or router must handle either IPv4 or IPv6 or both, called dual stack separately. So remember the dual stack for the router or network layer 3. Earlier, those must support either the IPv4 or IPv6 converted to IPv4 or vice versa to support the other or IPv6 protocol from IPv4, because the only similarities in their header fields are version. The Internet Header Length (IHL) field is the number of 32-bit words in the IPv4 header, including any option. So this IHL is also a number, and particularly this number represents the 32-bit words in the IPv4 header, including the option or additional option that it might have. Because this is also a 4-bit field, which is this 4 bits, the IPv4 header is limited to a maximum of 15 32-bit words or 60 bytes. So if we convert that, this 4-bit is limited to a maximum of 15 32-bit words or 60 bytes. Later, we shall see how this limitation makes some of the options, such as record route option, nearly useless today. So a record route option, which usually in this part, the option file part, are nearly useless today. Following the header, the normal value of this field when no options are present is 5. So for IHL, the normal value is 5. There is no such field in IPv6 because the header length is fixed at 40 bytes. So the reason why the only reason why you have IHL, because it is allowed to have greater number of length or a header length. So IPv6 doesn't have that because it is fixed in at 40 bytes. Following the header length, the original specification of IPv4 RFC 0791 specified a type of service. Byte and IPv6 specified the equivalent traffic class byte. So these were the old way, which is this, the DS field and the ECN. It used to be called TOS and the traffic class byte for IPv6. Use of this never became widespread, so eventually this 8-bit field was split into smaller parts and redefined by a set of RFCs. RFC 3260, RFC 3168, RFC 2474, and others. The first 6 bits are now called the Differentiated Services Field, DS field, and the last 2 bits are the explicit congestion notification. So this 8-bit was split into 2 parts, such as the first 6 bits are now called DFS or DS field, Differentiated Services Field, and the last 2 bits are the explicit congestion notification. So this congestion, you might have imagined that it is used for congestion traffic, and sometimes this differentiated services field are used for prioritization. So ECN field or indicator bits, these are our RFCs now applied to both IPv4 and IPv6. So as we can see, we also have that ECN and DS field in IPv6. These fields are used for special processing of the datagram when it is forwarded. We discuss them in more detail in the future videos. The total length is the total length of the IPv4 datagram in bytes. So here's the total length. Using this field and IHL field, we know where the data portion of the datagram starts and its length. So using this total length, this is how we know where the datagram starts and how and its length. So it's only it's for total length is only for IPv4. Because this is a 16-bit field, the maximum size of an IPv4 datagram, including header, is 65,535 bytes. So the maximum datagram or size of a datagram is actually 65,535 bytes because of this 16-bit field total length parameter. When you convert this 16-bit, you would get 65,535 bytes. The total length field is required in the header because some lower layer protocols that carry IPv4 datagrams do not accurately convey the size of encapsulated datagrams on their own. So the reason why it was created is because the lower level sometimes do not accurately determine the size. Ethernet, for example, pads small frames to be a minimum length 64 bytes. So remember in the previous video, the Ethernet actually adds 0 to make it a minimum of 64 bytes, or the MTU, right? So even though the minimum Ethernet payload size is 46 bytes, an IPv4 datagram can be smaller as few as 20 bytes. If the total length were not provided, the IPv4 implementation would not know how much of a 46-byte Ethernet frame was really an IP datagram, as opposed to padding, leading to possible confusion. So the Ethernet, remember, its IP datagram are being padded if it doesn't meet the minimum 46 bytes. So let's say it only has 20 bytes. So those additional 26 bytes are added. Without this, the destination packet would not know how much or the total length of this packet. Although it is possible to send a 65,535 byte IP datagram in this 16-bit total length, most link layers such as Ethernet are not able to carry one this large without fragmenting it, chopping it up into smaller pieces. So most link layer such as Ethernet, though it provides this large size, are actually not able to carry this large without fragmenting or chopping it into smaller pieces. Furthermore, a host or one that has CPU memory or the application layer would not know how much of a 46 byte, furthermore, a host is not required to be able to receive an IPv4 datagram larger than 576 bytes. In IPv6, a host must be able to process a datagram at least as large as the MTU of the link to which it is attached. So that's 46 bytes. And the minimum, for IPv6, the minimum MTU is 1280 bytes. Many applications that use UDP protocol, see chapter 10 for data transport like DNS, DHCP, etc., use a limited data size of 512 bytes to avoid the 576 byte IPv4 limit. So you really get this limit in the host part. and the transport, because they are the one on this higher level. TCP chooses its own datagram size based on additional information. When an IPv4 datagram is fragmented into multiple smaller fragments, each of which itself is an independent IP datagram. When an IPv4 datagram is fragmented into multiple smaller fragments, each of which itself is an independent IP datagram. So if an IPv4 is fragmented, it will be treated as an independent IP datagram. The total length field reflects the length of the particular fragment. So when we fragment a packet, the length of that packet or IP datagram will be the length of that actual packet that was divided. Since remember, it only has 576 bytes, and it is connectionless, meaning an a B could go first, then A, or a B could arrive first, then A. Therefore, those individual packets represent different length or total length. Fragmentation is described in detail along with UDP in Chapter 10. In IPv6, fragmentation is not supported by the header, and the length is instead given by the payload length field. Fragmentation described in detail along with UDP in Chapter 10. In IPv6, fragmentation is not supported by the header, and the length is instead given by the payload length field. So there is no total length in IPv6. It's only in the IPv4. So as you can see, we have payload length for IPv6. This field measures the length of the IPv6 datagram, not including the length of the header. So it's only the data, not the header. Extension headers, however, are included in the payload length field. So consider the header like the first one, the metadata that identify the actual data or helps identify the actual datagram, kind of like an Ethernet frame, the FSD and the preamble and the destination and the source. So those are the headers, and also these are the top from, let's see. Here is the IPv6. So these are the header until source and destination. The options in IP data is, if any, is not included. So this field measure the length of the IPv6 datagram, not including the length of the header. So the payload length measure the length of IPv6 datagram, which is this. So these are the header. This payload length is the actual datagram. Let me see. Yeah. As with IPv4, the 16-bit size of the field limits its maximum value to 65,535. So just as the total length, it also has limited value of 535 bytes. With IPv6, however, it is the payload length that is limited to 64 kilobytes. Not the entire datagram. So the 64 kilobytes or 65,535 bytes limit for the IPv6 is the payload length, not the entire diagram. Because remember, this field only measures the length of the IPv6 datagram, not including the length of the header extension headers, however included in this. So in addition, IPv6 supports a jumbogram option, see section 5.3.1.2, that provides for the possibility, at least theoretically, of a single packets with payloads as large as 4 gigs. So it also supports a 4 gig, which is called jumbogram. The identification field helps identify each datagram sent by an IPv4 host. So this identification, which is the 16 bits as well, identify each datagram sent by an IPv4 to ensure that the fragments of one datagram are not confused with those of another. So this is what the identification is for, to distinguish these fragments of one datagram are not confused with of another. The sending host normally increments an internal counter by 1 each time a datagram is sent from one of its IP addresses and copies the value of the counter into the IPv4 identification field. So this is how a sending host increments internal counter by 1 a datagram from one of its IP address and copies value of the counter into the IPv4 identification field. So the sending host that was received like another half from a router or switch will increment it and copy it into this identification. This field is most important for implementing fragmentation. So to implement fragmentation, these are the most important. So we explored further in chapter 10, where we also discussed the flags and fragment offset fields. these flags and fragment offset, we will discuss that further in chapter 10. In IPv6, these fields show up in fragmentation extension header. So this identification are in the fragment extension header, which we will discuss later in the next video. So there's an identification in IPv6, but it's a different vocabulary or different name or description, kind of like the total length as opposed to the payload length. The time to leave field or TTL of IPv4 sets an upper limit on the number of routers through which a datagram can pass. It is initialized by the sender to some value. So it is initialized by the OS host to some value. 64 is recommended, although 128 or 255 is not uncommon, and decremented by 1 by every router that forwards the datagram. When this field reaches 0, the datagram is thrown away and the sender is notified an ICMP message. So when this field reaches 0, when it was thrown away, remember the ICMP is the one being used to send an error or an update what happens on the packet. Note the TTL field was originally specified to be a maximum lifetime of an IP datagram in seconds, but routers were also always required to decrement the value by at least 1 because virtually no routers today hold on to a datagram longer than 1 second under normal operation. The earlier rule is now ignored or forgotten, and in IPv6 the field has been remained to its de facto use hop limit. The protocol field in the IPv4, which is this after time to leave, it's also 8 bits, contains a number indicating the type of data found in the payload portion of the datagram. The most common values are 17 for UDP and 6 for TCP. So another thing is that time to leave has 8 bits and protocol is 8 bits, and just like with IPv4 and IPv6, it also used number such as 17 for UDP and 6 for TCP to identify the type of data it used. This provides a demultiplexing feature so that the IP protocol can be used to carry payloads of more than one protocol type. So these are the available features that you can activate configured in the upper layer, but by default it is not configured, just like what we discussed in the previous video. It's up to you to activate these features. Although this field originally specified the transport layer protocol datagram, the transport layer protocol, the datagram is encapsulating. It is now understood to identify the encapsulated protocol, which may or not be a transport protocol. So remember, the transport protocol are being encapsulated into the IP layer 3. These fields are used to identify or to help identify which type of data, kind of like a de-identification bits, but I mean it's not identification, it's just used to identify, but it's not an actual guarantee. For example, other encapsulations are possible, such as IPv4 in IPv4 value 4. So these are not transport layer protocol, but those are possible as well, kind of like encapsulation within IPv4. The official list of the possible values of the protocol is given in the assigned number page, or AN. The next header field is the IPv6 header. The next header field in the IPv6 header generalizes the protocol field from IPv4. So it is similar to the protocol field in this, but it generalizes it further for IPv6. It is used to indicate the type of header following the IPv6 header. So it's used to indicate the type of header, just like the protocol in IPv4. This field may contain any values defined for the IPv4 protocol field, or any of the values associated with the IPv6 extension header described in the future video. So remember, the protocol has the TCP or UDP. This is where the next header, along with the other along with the other extension header or other possible identification that will identify the data in that upper layer will be discussed in the next video. The header checksum field is calculated over the IPv4 header only. So the checksum is only calculated using this IPv4 header, which is this part. This is important to understand because it means that the payload of the IPv4 datagram, like TCP or UDP data, is not checked for correctness by the IP protocol. It's only the header. So remember, the IPv4 protocol has this option, if any, variable length. Let's see. The IP data variable length, such as the UDP, etc. The actual data, so it's not the header. Those are not described here in checksum. So that's why those TCP or UDP data has their job in checking its correctness, usually using its payload length or data and header and other measurement. So to help ensure that the payload portion of an IP datagram has been correctly delivered, other protocols must cover any important data that follows the header with their own data integrity checking mechanism. We shall see that almost all protocols encapsulated in IP, ICMP, IGMP, UDP, and TCP have a checksum in their own headers to cover their header. So almost all protocols encapsulated in IP, like ICMP, IGMP, UDP, TCP, have a checksum in their own headers to cover their header. So aside on top of this checksum for this header, they have their additional checksum to double check and the data, and also to cover certain parts of the IP header they deem important, a form of layering violation. Perhaps surprisingly, the IPv6 header does not have any checksum field. So IPv6 does not have checksum field. So note, omitting the checksum field from the IPv6 header was somewhat controversial decision. The reasoning behind this action is roughly as follows. Higher layer protocols requiring correctness in the IP header are required to compute their own checksums over the data they believe to be important. A consequence of errors in the IP header is that the data is delivered to the wrong destination, is indicated to have come from the wrong source, or is otherwise mangled during delivery. Because bit errors are relatively rare, thanks to fiber optic delivery of the internet traffic, and stronger mechanisms are available to ensure correctness of other fields, higher level checksum, or other checks, it was decided to eliminate the field from the IPv6 header. The algorithm used in computing a checksum is also used by most of the other internet-related protocols that use checksum. So the algorithm used in computing checksum of the header are also used by other internet-related protocols that use checksum, and is sometimes known as the internet checksum. Note that when an IPv4 datagram passes through a router, its header checksum must change as a result of decrementing the TTL field. So when you hop one router, the header checksum must change as a result of decrementing the TTL field, because again the TTL has the maximum routers, usually 64 or 128 or 255. We discussed, so basically as we decrement the TTL, we also change the checksum. We discussed the methods for computing the checksum in more detail in section 5.2.2. Every IP datagram contains the source IP address of the sender of the datagram and the destination IP address of where the datagram is destined. These are 32-bit values for IPv4 and 128-bit values for IPv6, and they usually identify a single interface on a computer. So it's usually this identifies single NIC or network interface on a computer, although multicast and broadcast addresses, see chapter 2, violate this rule. So version 4 bits. Purpose, it indicates, let's just go over through what this means. So it indicates which version. Oh my god, you didn't screenshot the right. Let me just wasn't able to screenshot it properly. Yeah, so version, let's just expand a little bit. The purpose, it indicates which version of IP is used. This tells the receiver how to parse the rest of the header. For 4, value is 0100, for IPv6 0110. Notes, meaning IPv4 notes variable header length 20 to 60 bytes. So the options that we discussed could be up to 60 bytes. IPv6 fixed header length 40 bytes. Because only the position of the version field is the same, IPv4 and IPv6 are not binary compatible. You must know the version first to interpret the rest. IHL, Internet Header Length, 4 bits, IPv4 only. It tells how long the IPv4 header is in 32-bit words, like value 5, meaning 5 times 4 equals to 20 bytes, no option. So example, standard, value 6 to 15, meaning 24 to 60 bytes, with options. Example, it's rare today. So that's the value. It's still a number in this internet header length. It tells you how many words or how long the IPv4 header is in 32-bit words. So IPv6 omit this field. Its header is always 40 bytes. This makes packet parsing simpler for hardware and routers. So it's still a number 5 and then 6 to 15. DS field and ECN, 8 bits total. Historically called TOS, type of service in IPv4, now redefined by multiple RFCs. Bits 0 to 5, field differentiated service code point, DSCP. Function used for cost, quality of service, like prioritize VoIP or video. So this is what I was talking about with the DS field. So if the bits are 0 to 5, it means it's for differentiated service code point or DSCP. Now the function of this is to configure a quality of service, like prioritize VoIP or video. So this is how you create those voice over IP video. For bits 6 to 7 field, explicit congestion notification or ACN used for congestion control. Routers mark ECN bits instead of dropping packets. So if say you want to um, control the congestion, the router will see these bits and it will mark it instead of dropping the packets. IPv6 calls the whole byte traffic class, but meaning is identical. So it's still the same meaning, and also the whole byte is called traffic class in IPv6, not type of service. Example in a router, DSCP46, the binary is 101110, expedited forwarding, EF for lower or low latency traffic. For ECN bits, 10 is equals to congestion experience. So those value or bits 10 signifies that there's a congestion in that sending router. Total length for 16 bits, IPv4 only. Purpose, it specifies total size of the IP datagram in bytes, like header plus data. So it's just not the datagram, the actual datagram, because this is the content of the data. The header is again a metadata, and this is the one that has a maximum 64 kilobytes. Typical is 576 byte IPv4 minimum reassembly buffer, and 1500 for Ethernet MTU. IPv6 replaces this with payload length 16 bits, length of everything after the fixed header. So it doesn't include the header. Sorry, it includes the header as well. The total IPv6 packet size is equals to 40 the header plus payload length. Sorry, the header is not actually included here in payload length for IPv6. While in IPv4, its data, or kind of like the payload of IPv4, and the header is included in the total length. So example, field header IPv4 variable 20 to 60 bytes. IPv6 fixed 40 bytes. Length field, total length, header plus data. For IPv6 payload length, data only. IPv6 also has a jumbogram extension, 32-bit length for 64 kilobytes payload. Identification, 16 bits, IPv4 only. Labels each datagram uniquely so that fragments can be reassembled. Each outgoing IPv4 packets gets an incrementing ID. So this is how you increment. If a packet, this is how the router increment, so that all the packets are identified uniquely using an incrementing ID. If a packet is fragmented, all fragments share the same ID. So let's say you fragment a same conceptually the same packet. Those will have the same ID for identification because they were just divided due to the limits of the maximum host receiving data. Now the receiver uses SRC IP, DSD IP protocol, and then the ID to group the fragments. So these are the, aside from protocol, these identification are used by the receiving router to group all those packets that conceptually the same. Now IPv6 moves this to an optional fragment extension header, only used if fragmentation occurs. So since IPv6 support like 1 to 80 bytes, sorry, a larger, significantly larger bytes than IPv4, it uses an optional fragment extension header, which is only used if fragmentation occurs on it. Flags 3 bits plus fragment offset 13 bits used only in IPv4 fragmentation. For flag, bits 0 meaning it's reserved. For bit 1, DF, don't fragment. For bit 2 in flags, MF means more fragments, set on all except last fragment. Fragment offset gives the byte offset over 8 of these fragments data relative to the start. IPv6 router never fragment packets. Only the source host may do so using the fragment header. So this is also why it uses a fragment extension header, because IPv6 router never fragment packets. Only the source host may do so using the fragment header. Time to live, TTL 8 bits purpose prevent infinite looping of packets initialized by sender, commonly 64, 128, or 255, decremented by 1 per router hop. When it hits 0, router drops the packet and sends ICMP time exceeded back. IPv6 renames it to hop limit, same function. Protocol 8 bits IPv4. Next header for IPv6, it's also the same as 8 bits. Tell IP how to interpret the payload. Example 1, value ICMP. Example 6, value TCP. Example 17, value UDP. So this one value in this protocol are what you get when you hit the TTL0. Example 4, value IPv4 encapsulation. Example 41, value IPv6 encapsulation. Example 47, GRA. Example 50, ESP or IP6. IPv6 uses next header instead, same 8-bit space, but can chain multiple extension headers. So it can chain multiple extension headers, like it can chain all of this. Header checksum 16 bits IPv4 only. Purpose, it detects errors in the IPv4 header, not payload. So a header checksum only detects the error in the header, not the actual payload, which is the data that we discussed earlier that included in total length. Routers recompute it each time TTL decreases, so it's highly interconnected to the TTL. IPv6 removes it entirely, which make faster routing, assumes link layer CRCs handle integrity. So because of the fiber optic, which has this good CRC or the error prevention, IPv6 were able to remove it. Source address 32 bits and destination address 32 bits. Self-explanatory, the sender and receiver IPs, IPv6 expand them to 128 bits each, allowing 3.4 times 10 raised to 38 unique address. Options, variable IPv4 only, optional fields for record route. So these were the one we render useless because of those concept we discussed earlier. Timestamp, loose or strict source routing. So in case you need that, the timestamp and loose strict almost never used, though routers drop or ignore them. IPv6 replaces this concept with extension headers, cleaner and optional. Padding ensures header length is a multiple of 32 bits, 4 bytes, usually zeros. So the padding means the header length is a multiple of 32 bits, which is 4 bytes. You will need to add the 0. IPv4 header layout summary. So here 0 to 31 version, type of service, destination option, and the padding to make the fragment offset, identification, the version, the protocol, header checksum, source address, destination option, padding, layout summary, payload length. So you don't have the data yet here from the upper protocol, which is the TCP, where the 13 bits are flags plus fragment offset. In the IPv4 header, bytes 6 to 7 counting from 0 hold flags and fragment offset after the identification of 16 bits. Bit layout inside those 16 bits. You have this RDM, R, bit 0 equals to reserve, must be 0. D, bit 1 equals to don't fragment. M, bit 2 equals more fragments. Example of offset is bits 3 to 15. Offset over 8 bytes from start of original payload. Example, flags plus offset equals 0x2000 001 0000002. DF equals to 0. MF equals to 1. Offset equals to 0. So that packet has more fragments coming. MF equals to 1, and it's the first piece. Why IPv6 never fragments packet in routers? So why it never fragment? So that's the question we have earlier. IPv4 routers were allowed to fragment large packets in the middle of the network, but this caused extra CPU work for routers because they need to reassemble that. They need to track the protocol, the ID, source, and destination for each fragment that has the same ID and protocol and source and destination. Reassembly at the destination, expensive, unpredictable performance, and loss. If one fragment drops, whole datagram fails. So even if one of that fragment drop, the whole datagram fails. So again, that fragment is part of the whole datagram of this layer 3. So IPv6 remove router fragmentation completely. Instead, the router must drop packets larger than the link MTU. They send back an ICMP6 packet too big message to the sender so that the sender know that it sent a packet larger than the link MTU, which is larger than IPv6. Usually those are enough to send the datagram. The sender then performs path MTU discovery or PMTUD and resend smaller packets. So it's up to the sender to fragment its header. Only the source host may fragment IPv6 packets, and only if it adds a fragment header extension. So these fragment extension are only used if you really need or the host really need to chop it. But again, it came from the host, not in the middle of the hop along the network, just like in IPv4. IPv6 fragment header structure. Next header, reserve, fragment, offset, res, and then after that is identification. Next header, what comes after this, like TCP, fragment offset, the 13 bits, same concept as IPv4. M bit, more fragments, meaning, so identification 32 bits, same purpose, it ties fragments together. The receiver reassemble using the identification field. So IPv6 kept the concept but moved it out of the main header and restricted who can use it. So it kept the same concept, or the fragment header structure kept the same concept but moved it out of the main header and restricted who can use it. Options and padding in IPv4 and IPv6. Feature options, IPv4 part of the header after 20 bytes variable length. IPv6 remove, replaced by extension headers. Padding 0 bytes at the end of the header to make multiple of 32 bits. IPv6 not needed, fixed 40 byte base header. IPv4 layout example, option type, option length, option data, more option, 0 padding. Examples include record route, timestamp, security, source route. Routers often ignore or drop this today because they slow down forwarding. So this record route, timestamp, security are usually automatically disabled in modern router because they slow forwarding. IPv6 equivalent extension headers. Each header is a separate structure chained via the next header field. Common ones, hop by hop options. So the IPv6 extension header are each header is a separate structure chained via the next header field. Common ones is hop by hop options, routing header, fragment header, destination options, AH/ESP, IPsec. Each is a multiple of 8 bytes, so no arbitrary padding needed. How layer 3 connects to layer 4? Code view. Let's simplify the logic that happens when a packet moves upward in the stack. So inside Linux kernel sudo path. First, it called from network driver after receiving Ethernet frame. Net if net ifs underscore receive underscore skb struct sk underscore buff skb. Inside this is eth underscore type underscore trans argument skb comma dev. It identifies ether type 0x0800 equals to IPv4, 0x86 dd equals to IPv6. IP underscore receive argument skv comma dev comma pt underscore prev comma orig underscore dev for IPv4, then close. Now for IPv4 input handler, int IP underscore RCV with an argument struct sk underscore buff asterisk skb comma struct net underscore device asterisk deb, and then struct IP version. So basically this this is what the OS does, or Linux OS does. If it was called from its network driver after receiving Ethernet frame from its network driver, let's say from the port, right, physical to layer 2, now it's a network driver. This is the call for that. Now IPv4 input handler, so the int we discussed has inside this if IPH version not equals to 4, or if it's not IPv4, drop. If checksum underscore bad IPH, drop. If dash dash IPH TTL equals to 0, send ICMP underscore time underscore exceeded. So this is how you send ICMP that has the value of 1. Then after that, demultiplex by protocol layer 4, switch IPH protocol, case iproto underscore TCP underscore v4 underscore RCV, argument skb, break, case iproto underscore UDP, and then semicolon, and then UDP underscore RCV skb, then break, semicolon, case iproto underscore ICMP, semicolon, then next line ICMP underscore RCV, argument skb, then next line break, close. So layer 4 example, int UDP underscore receive, argument struct sk underscore buff asterisk skb, inside it is struct UDP HDR asterisk UH equals to UDP underscore. So these are the code for layer 4. After that, layer 3, int UDP underscore RCV struct and then inside it struct UPHDR asterisk UH equal UDP underscore HDR skb. Then next line, deliver underscore to underscore socket argument UH to dest underscore port, then skb to data. So and then close. So the IPv4 protocol field tells which function pointer to call, TCP, UDP, ICMP. So this code that we have in switch case tells which function pointer to call, TCP, UDP, ICMP, which has their own modules, or functions inside the Linux kernel. The payload pointer in the socket buffer (skb) is advanced by IHL times 4 bytes. The OS kernel network stack is modular. Each protocol registers a handler for its number. How layer 2 connects to layer 3? Ethernet frame, destination MAC, SRC MAC, ether type, and then payload, then CRC. If ether type equals to 0x800, pass to IP underscore RCV, which is the IPv4. If ether type is equals to ZR, so it used the if else statement using the ether type. So as you can see, you have destination and SRC and ether type here, and based on that, it is passed on the associated function handler for IPv4 IPv6. So for if ether type equals to 0x86DD, pass to IPv6 underscore RCV. These are registered via the ether type protocol handlers in kernel networking subsystem. Visual connection layer 2 to 3 to 4. Ethernet frame, MAC header, it has the payload and then the IP datagram. So ether type 0x0800 to IPv4 header version. The IPv4 header has a version /IHL/TTL/protocol, and it has the payload, the TCP or UDP data. So that's the payload we're talking about. The total length we discussed, that's header plus data. It is the TCP or UDP data. Then for TCP and UDP header, we have application data. Now in user space, how the OS exposes it, application don't see these headers, they use sockets. So for application, you have int sock equals to socket, argument AF underscore init, comma, sock underscore dgram underscore iproto underscore UDP, semicolon, next line, send to argument sock, comma, data, comma, len, comma, 0, comma, end, ADDR, comma, size of argument ADDR. Then the kernel will build from that application request UDP header to IPv4 header to Ethernet frame, then pushes it to NIC driver queue to be able to send to other port. Now if HDRINCL is set to raw socket, user code can build its own IPv4 header manually used in traceroute, etc. So these are the another diagram. NIC to kernel driver to IP layer that has this fields, and then to if IPv6, this it was sent to IPv6, and then transport if it's IPv6, this is what you get, and then you send to the transfer layer, source, destination, length, and then the socket. So socket, again, that's kind of like the netlink. It is used to tap into the kernel by application. The internet checksum. The internet checksum is a 16-bit mathematical sum used to determine with reasonably high probability whether a received message or portion of a message matches the one sent. So this is how you use the checksum header. So it uses whether a received message or portion of a message matches the one sent. To compute the IPv4 header, checksum for an outgoing datagram. The value of the datagram checksum field is first set to 0. So to compute like the header checksum you will use when sending an IPv4 header and data, the value of the datagram's checksum field is first set to 0. The 16-bit ones complement sum of the header is calculated, or the 16-bit ones complement sum of the header is calculated. The entire header is considered a sequence of 16-bit words. So it's first set to 0, then a 16-bit complement sum of the header is calculated. The entire header is considered a sequence of 16-bit words. So it first set to 0 and then a 16-bit ones complement, which we will discuss further. The 16-bit ones complement of this sum is then stored in the checksum field to make the datagram ready for transmission. Ones complement addition can be implemented by end round carry addition. So this ones complement
can actually be implemented using an end-round carry addition. When a carry bit is produced using conventional 2's implement addition, the carry is added back as a 1 value. Now figure 5.3% an example where the message content as represented in hexadecimal. So figure 5.3, the internet checksum is the one's complement of one's complement 16-bit sum of the data being checksummed. Zero padding is used if the number of bytes being summed is odd. If the data being summed includes a checksum field, the field is first set to 0 prior to the checksum operation and then filled in with computed checksum. To check whether an incoming block of data that contains a checksum field, header, payload, etc. is valid, the same type of checksum is computed over the whole block, including the checksum field. Because the checksum field is essentially the inverse of the checksum of the rest of the data, computing the checksum on correctly received data should produce a value of 0. When an IP datagram is received, a checksum is computed across the whole header, including the value of the checksum field itself, assuming there are no errors. The computed checksum value is always 0, a one's complement of the value FFFF. Note that for any non-trivial packet or header, the value of the checksum field in the packet can never be FFFF. Note that for any non-trivial packet or header, the value of the checksum field in the packet can never be FFFF. If it were, the sum prior to the final one's complement operation at the sender would have to have been 0. No sum can ever be 0 using one's complement addition unless all the bytes are 0, something that never happens with any legitimate IPv4 header. When the header is found to be valid, the computed checksum is non-zero, the IPv4 implementation discards the received datagram. No error message is generated. It is up to the higher layers to somehow detect the missing datagram and retransmit if necessary. Where this happened in the stack. So let's revisit your stack from before. Application, transport layer, TCP, UDP, network layer, data link, Ethernet, bridge or RSTP, NIC hardware. The internet checksum is computed at the network layer, specifically for IPv4 headers only. So it is done in IP or layer 3, specifically for IPv4 headers only, because IPv6 does not have checksum. It relies on the fiber optics and the TCP or the higher level protocols. When the kernel's IP layer constructs an outgoing datagram, it fills in the IP header fields, version, IHL, total length, TTL, protocol, etc. It computes the header checksum. So again, when it's constructing an outgoing datagram, it fills in first the version, IHL, total length, TTL, protocol, etc. Then it computes the header checksum using this one's complement math. Then it passes the datagram down to the NIC driver for transmission, or in layer 2 and layer 1. What the checksum is and isn't. The checksum is not like Ethernet CRC, which is stronger and done by hardware at layer 2. Ethernet layer 2 uses CRC32, detects bit errors on the wire. IP layer 3 uses a 16-bit ones complement sum, weaker but fast to compute in software. So it's a software, it uses 16-bit ones complement sum, but it's fast. It's meant to catch random corruption inside router's memory, buffer, or software stack, not noise on the cable. That's CRC's job. Where it fits with what we discussed, bridges, STP, RSTP, etc. Everything below IP, bridges, VLANs, RSTP, MVRP, etc. work with frames. Each frame encapsulates the IP packet unchanged, meaning when a bridge forward the frame, it does not modify or recompute the IP checksum. If the bridge or router did modify any IP header field, like decrementing TTL, it must recompute the IP checksum. So this TTL on IPv4 is highly related to the IP checksum. So for example, router receive packet, it decrements TTL, recompute IP header checksum, and then forwards it. The checksum update happens in the router's kernel IP forwarding logic. So the checksum update happens in the router's kernel IP forwarding logic. Or in a layer 3, often in a tight C using C loop that adjusts the checksum incrementally. How it connects upward to the transport layer. Transport protocol like TCP, UDP, ICMP also have their own checksum that protect their payloads and include parts of the IP header, pseudo header. For IPv4, checksum only the header. TCP or UDP, checksum header plus data plus parts of IP header. So as you can see, in TCP, you have a checksum header. You also have parts of IP header as well as the data. That's why it's able to provide a better error control than layer 3. That's why if the IP checksum passes but a bit in your payload flip, the IP layer won't notice, but TCP or UDP will. How the code actually looks in Linux kernel simplification. Simplified pseudocode of the IPv4 header checksum, like underscore sum 16 IP fast, so simplified pseudocode, underscore sum 16 IP underscore fast underscore csum cons with an argument cons void asterisk IPH comma unsigned int 1H1 IHL rather, and then inside it is unsigned long sum equals to 0 semicolon, then cons u16 asterisk ptr equals to IPH, then for loop for argument int 1 int I equals to 0 semicolon 1 less than IHL asterisk 2 semicolon I plus plus. Inside it is sum plus equal NTOHS argument ptr and I. End around carry, so this is how you do the end around carry and the kind of like the C loop. So while argument sum greater than 16, inside it is sum equals to argument sum and 0xFFF plus sum greater 16 semicolon, then return h tons, which is the sum. So these run inside the kernel's IP output function. So kernel's IP output function, the kernel IP function module before it's sent to the NIC. On receive, the same logic is done in reverse. The checksum is verified, and if the result isn't 0 or invalid, the packet is dropped silently. IPv6 connection. IPv6 completely remove this header checksum. Reason, it slows down forwarding. Routers must recompute it every hop. Link layers already have CRC. Transport layers still have their own checksum anyway. So IPv6 relies on Ethernet CRC layer 2, TCP or UDP checksum layer 4, and skips the IP level checksum. That's why IPv6 headers are simpler and faster to process. Verification and visualization. If you open Wireshark in IPv4 packets, you'll see a field called header checksum. It shows header checksum 0x1AFF if correct, if verified. In IPv6 packets, that field is absent. You can think of it as a tiny built-in self-check every router does at the IP layer, right between Ethernet CRC check or hardware and TCP's checksum software end-to-end. So what's actually happening conceptually? When the kernel prefers an IPv4 packet, it takes the header bytes only, not payload, adds them as a sequence of 16-bit words. So it takes the header bytes, not the payload, because remember the total length is header and the data. So this header bytes is added as sequence of 16-bit words. Uses ones complement arithmetic, not normal 2 complement addition. So the C loop that we have discussed earlier The while takes the ones complement of the total sum, puts that value into the checksum field in the header. Takes the one complement of the total sum and then puts that value in the checksum field in the header. When a router receive gets the packet, it recomputes the same checksum over the entire header, including the checksum field itself. If the result is equals to 0xFFFF, which is all ones, like ones complement 0, the header is correct. So if the result is equals to 0xFFFF, which is all ones, like ones complement 0, the header is correct. If not, discard the datagram silently. Why end around carry addition is needed? Like we discussed in the code. In normal 2 complement math, overflow bits are discarded. 0xf like 0xff plus 0x0001 equals to 0x0000. But in one's complement, the overflow wraps around and it's added back in, like 0xFFFF plus 0x0001. 2 carry equals to 1, 2 result equals to 0x0000 plus 1 equals 0x0001. That's what end around carry addition means. So every time the sum goes beyond 16 bits, you add the overflow back into the low end. Mapping the book's example to this logic. So let's annotate your quoted example. Step 1. Operation message E3 4F 2396442799F30000. Result none, meaning 16-bit words or header fields. Step 2. 2 complement sum equals to 1 E4FF. Result overflow bit equals to 1, meaning row binary sum before wrap. Step 3. Add carry bit end around. E4FF plus 1 equals to E500. Result none, meaning this one's complement addition. Step 4. Take one's complement. E500 equals to 1AFF, meaning this is the checksum. Step 5. Fill the header checksum field with 1AFF. Result none, meaning header is now ready to send. Now at the receiver, step 1. Operation, add all 16-bit words, header plus checksum. Result FFFF. Step 2. Operation, one's complement of result equals 0000. Result valid header. So if the receiver computed sum equals to FFFF, the one's complement FFFFF equals to 0 is valid. So in Linux kernel simplified pseudocode, this snippet does exactly what the math describes. So U16 IP underscore checksum, argument U16 asterisk buff, comma int len. Inside this is U32 sum equals to 0, then while len is greater than 1, inside it is sum plus equal asterisk buff plus plus. Then inside this is if sum and 0x1000. Inside this is sum equals to sum and 0xFFFF plus 1 semicolon, which is the end around carry. The if sum and 0x1000 is the if carry out of 16 bits, and then sum equals to sum and 0xFFFF plus 1 is the end around carry, and then close. Next line, len minus equal to semicolon, then close. If len, so if add number of bytes, then sum plus equals asterisk U8 asterisk box semicolon. Then final fold and complement, while sum greater 16, next line sum equals to sum and 0xFFF plus sum greater 16, then return sum. Closing. So that's implementation of your textbook end around carry plus 1 complement rule. So how it relates to everything we discussed earlier. The checksum logic happened inside the kernel IP layer right before it hands the datagram to the NIC driver. It's purely software, nothing to do with the bridge or RSTP logic at layer 2. But if an Ethernet frame carrying this IP datagram gets corrupted, the NIC would catch it with CRC first hardware check. If CRC passes but some in-memory corruption flips a header bit in software or router memory, this IP checksum would detect it. Finally, if both CRC and IP checksum pass but the payload got corrupted in transit, TCP or UDP checksum at layer 4 would catch that. So it's part of the layered protection chain. So layer 2 mechanism CRC32 scope entire Ethernet frame performed by NIC hardware. Layer 3 mechanism IP checksum scope IPv4 header only performed by kernel software. Layer 4 mechanism TCP or UDP checksum scope header plus payload plus pseudo header performed by kernel software.